I should say lecture portion of the day, not the exam portion of the day, kind of picking up where we left off last time. Now, just to remind you, we were doing these closed cell torsion problems. We define a cell as an enclosed, thin-walled section. It's a closed cell if it wraps around and comes back on itself in a complete loop. It's open if there's a little notch there. And we're going to talk about open cells in a little while. This is a closed cell like a cylinder or similar. And of course, we defined a tangent normal system. We went through, we did equilibrium. We differentiated the fact that the shear flow calculation is based on beam bending. If we have no beam bending in the problem, what we get is a circumstance where Q within the cell is going to be constant. Okay, Q is constant, so we defined that. And of course, I wanted to remind you that what is Q? Q is the shear stress times the thickness. Okay, and we ended up here at this. This was the calculation that basically supports that as we're going around this closed cell, there's this reciprocal relationship between stress and thickness. Because the two of them are constant, if your thickness changes, your shear stress will change. If your shear stress changes, it's because your thickness changed. So that is this interesting phenomenon about shear flow as we go around this closed cell for the torsion problem. Now, we said it was constant. Here's the next thing that we need to do. We need to recognize, of course, well, what is shear flow, right? Shear flow is shear stress times thickness. What's its unit? Its unit is force per unit length. Now, if we take a look at a cross-section here, we can see at any position within this cross-section, we have a differential length ds in the s direction. So a small increment in the s direction. And because this has a shear flow on it, there is a force per unit length over this differential length. So that's a differential force. Note also that that force is now at a radius from what we're calling the center of twist. So force times radius, well, that contributes a torque. And so we start to recognize that these shear flows in these closed sections contribute torque and ultimately are what cause us to be able to carry torques in these closed cells, these shafts, these box beams that are structurally there for, in the wings to carry the loads. Of course, in this context here, we're going to call R the position vector of the differential force. And again, it's measured from a point in the cross section. Really, it's measured from the center of twist. For our current purposes, it turns out that is going to not be of great concern, that we know where that center of twist is at any given moment. I'll tell you why in a few minutes. Keep in mind that the radius is a vector. As we go from one point to another in an XY space, that has components, so it's a vector. Q is a shear flow, force per unit length. Force per unit length. ds is a vector itself, so it has a direction associated with it. So force per unit length times ds times length is going to be a differential force, so that also is a vector. And keep in mind that they're not perpendicular. What do I mean by that? Well, that's pretty simple. So if I take even just a box section and I identify a point on that section, we'll say that this is that point. Here's the radius. Here is the direction of QDS. And obviously, as we're going around, it's not always going to be perpendicular. It will be perpendicular here at this point. It will not be perpendicular here at this point. So it's not always perpendicular. Okay, now of course the resulting shear force on the cross section, we need to recognize there is a shear force and there's a torque. So the shear force, well, what is shear force? Shear force is the integral of all the differential forces. And so here in this context, what we're doing is we're integrating around, for example, here the circle. So here I have a ds, a differential force here. I sum that to the other differential forces at every different location. Each one of them is a vector and has a magnitude. I sum, i.e. integrate. I integrate over the entire domain. And what do I know? Well, I know that that integral is going to be equal to 0. How do I know? Well, because this is a torsion problem. We have stated that we have a torque T. We said we're separating out the bending components that would be a shear resultant. So there is no shear resultant in this problem. It's only a torque. And so consequently, the integral of all the differential shear components has to be equal to 0. However, so that's true for this. So that is expressed as the integral of q ds. It is a closed integral from one point around to the other point. So it starts and finishes at the same point. So I'm using the closed integral sign. Closed integral of q ds is equal to 0. However, the resultant torque is not going to necessarily be 0. What's the justification for that? Well, this is, again, relatively simple. So as we're going around with a constant q, the direction is not going to change, and its contribution to moment or torque, so if I'm defining torque as positive this way, I'm defining shear flow as positive this way, and S as positive this way, then what we're going to find is that all of these, at every location, it is contributing a positive torque, differential torque, and then so when we integrate around the entire cross section, we're going to get a total torque that is going to be non-zero. So this is expressed in this way. So the differential force is R, I should say Q dot ds, so the differential length ds, Q, force per unit length. So this Q dot ds is differential force. So we're integrating R cross differential force, closed integral around the entire cross section. That's going to be equal to the torque. Okay, is that clear to everybody? I don't want to leave people behind. Please.
I have a question. How is that a cross product if there's a dot product there?
So Q dot ds is, Q is a vector, ds is a vector. Those are in the same direction, so that ends up being the dot product. The magnitude is going to be 1 there.
But isn't that a scalar?
Q dot, so we got, yeah, it is. So Q has units of force per length. Force per length, okay? And it only gets its direction when you then apply it in the length. So I misspoke there. You should not think of this as a dot product so much as just a multiplication. So that's a good catch. Who asked that?
David.
Ah, thank you, David. Thanks for catching that. Okay, so yeah. Anyway, so moving on. This is that calculation. Now, of course, we said Q was constant, so it comes out. And here's where you would have really gotten hung up if that were truly a dot product there. It's not. It's a multiplication. So it just pulls outside of the integral. Here I've drawn the radius to result to be in the positive quadrant just for this sake, and then I reoriented it so that ds is horizontal and the radius is off in a different direction. I did this in 2 different diagrams for a reason. So the reason for this diagram here is because I want you to recognize that this cross product ends up being a differential area. or it's going to be, I should say, related to a differential area, because we've got a radius which has a direction, we've got ds which has a direction. This creates a triangle between essentially what amounts to 3 points. So that can be expressed, this differential area is 1/2 ds times d. Again, be careful, this is just a times, it's not a dot product. 1/2 ds times d. Now d itself, this is 1/2 base times height, so that's the area of a triangle. D itself is related to the radius through the angle at which these two things intersect each other. So we're going to call that angle beta. And so this ends up being 1/2 ds r times sine of beta. So sometimes this is going to be perpendicular, sometimes it is not, but we're going to have this sine of beta. So when it is perpendicular, of course, that magnitude will be 1. When these two things are aligned, the magnitude will be 0 of the differential area. Now, why do I show you that? It's because then we can recognize that differential area is equal to, this is in magnitude, r cross ds. Because the sine of the beta is the cross product of the included angle. So 1/2 r cross ds. And then we can rearrange that to say that r cross ds is nothing more than 2 times the differential area of the triangle. Now, why is that interesting? Why is that used that way? Well, what this ends up telling us is that the area enclosed within this cross-section now is going to be directly related to the torque and the shear flow. Let me go to the next slide for you. Now I'm being a little bit more careful with my vector representation. Torque itself is a vector, so this is the magnitude of the torque. The direction vector in this case is the direction vector k, that is the one associated with the z direction. So this is equal to q times r cross ds, which is now q times 2a. The integral now, closed integral of dA is simply, sorry about the terribly sloppy handwriting with my mouse, this is just going to be a, right? So if this is 2dA, which of course it is, then this is going to be 2a, and so this integral ends up being equal to q times dA. I'm 2a, q times 2a, so the total torque is equal to 2 times the area enclosed times the shear flow. It's actually a really incredible statement. Okay? This is a really incredible statement. What do we learn? We learn that the shear flow itself, Q, the magnitude of the shear flow, well, it's directly proportional to the torque that's applied. It's inversely proportional to the area enclosed. Okay, this is, I think, in some ways counterintuitive. If I were to draw, a cross section, the shear flow is not related to the total material area, which I'm highlighting now. Rather, it's related to this area enclosed, the area where there is no material, really. That's incredible. It's really cool that as you enclose more area, you are decreasing the shear flow. And keep in mind that shear flow is constant. And as per David's question, it's a magnitude. It's a magnitude. And it only gets its direction when we're talking about the differential direction of S. So Nicole has asked a question in the chat window. Does the direction of Q change as you go around the circle? Yeah, yes, absolutely does. So, again, as you go around the circle, or it doesn't have to be a circle, the differential length ds has a different direction at different points in the circle. Here it's up and to the right, here it's basically to the left, here it's down and to the left. Since q is a magnitude, the vector qds is going to be different in direction at every point. Now, I shouldn't say at every point, because I got to be careful about that statement. So if I draw a square, then everywhere from here to here, the direction will be the same, and everywhere from here to here, the direction will be the same. But these are, it's all relative to the center of twist, and this radius to the center of twist now sort of defines how much of that shear flow contribution actually contributes torque. All right, so what's the takeaway? What do you think this means now? So Ron is asking a question. So the less material there is, the less shear flow you have. Well, now we got to be careful, Ron, because it's not necessarily that. What we're saying is the more area that's enclosed, the lower the shear flow. Now let me go back to a chalkboard. So here, if I take my circle and then I zoom in on just a portion of that circle. So here's a portion of the circle. Now the area enclosed should be interpreted as the area inside the midline. Okay. Now, so that's the interpretation of area. Now, what does this mean? That means that if this same circle that has the same sort of midline diameter, if it had a thinner material versus a thicker material, the shear flow is the same. The shear flow is the same. Now be careful, that doesn't mean the shear stress is the same. Right? We need to differentiate shear stress. So Q is equal to thickness times shear stress. So Q over thickness becomes shear stress. And so as the material gets thicker, the shear stress goes down. As the material gets thinner, the shear stress goes up. But the value of Q is the same. All right, so Nicole asks another question. But even though the direction changes, since Q is a magnitude, we can take it out of the integral. Not quite. So it's not because Q is a magnitude. It's rather because Q is a constant magnitude. Because it's a constant, it can come outside of the integral. And when I say constant, it's constant for this open, or I should say for this closed cell, right? We're going to amend that statement slightly later, but for now, that's the interpretation. It's constant within any given cell. Okay, so Ron says, that makes sense. Okay, good. I'm not seeing any more questions come across, so I'm going to assume we have some degree of clarity now. Feel free, again, ask questions, interrupt, chime in with the mic if I'm not seeing the chat window or if I've missed something that hasn't been answered by somebody else in the chat window. Okay, so anyway, bottom line, here's our solution. That is that Q is equal to the torque over 2 times the area. Now, if we are given the torque and we're given the geometry, we know shear flow, easy peasy. Right? That doesn't mean we're always given the torque, and sometimes this gets a little bit more difficult. We got to do some more manipulation. But if we're given the torque and we're given the geometry, we know the shear flow. Keep in mind, this is and this is the point that I was just making to Ron a moment ago. That is that the shear flow is what's constant. The shear stress is not. So the shear stress is going to be equal to the torque over 2 times the area enclosed times the thickness. So, torque over thickness then ends up being what's proportional to the shear stress. Now, keep in mind, we also have the material constitutive response. So if we have this level of shear stress, that means we're going to have this level of shear strain. Okay, we're using in this case the shear modulus rather than Young's modulus. You guys, of course, recognize that those two are related to each other. but shear modulus makes the most sense in this context. So the shear strain is equal to the shear flow over G times T. And of course, we know the relationship between Q and torque. So it's equal to the torque over 2G times A times T. So shear strain itself depends on the shear flow, the modulus, and the thickness. Now, as a general rule, in all cells, open and closed, we're going to find open cells don't have this constancy thing, or I should say not always have this constancy thing. The beam bending portions of it, the shear stress and strain are not going to be constant. Here, shear strain will not be constant because now it is a function of T. So if we have a cell that has a constant wall thickness, then the shear strain everywhere in that wall will be constant. But if it's a non-constant wall thickness, if it's varies as you go around, it's thicker here than it is here, then the shear strain is not constant. And we're going to say it's a function of S. That is the position within the cross-section in the tangent normal coordinate system. And of course, that means that it's also a function of X and Y if you're going back to the Cartesian system. Okay, now we've identified that there is a shear strain. Okay, now, oh shoot, I must have, here it is. Now keep in mind, and can you guys see me? I hope you can. This probably doesn't project terribly well, but as I am rotating my segment, we're getting twist, right? This thing is twisting and we're getting motion. And with motion, we get we're going to call it, in this case, I'll zoom in on the, no, that didn't help very much. In the S direction, I'm going to define an arc length. Basically, you can think of this as being a displacement in the tangent normal coordinate system where it is all tangent. So we're going to call that value US. Okay, so in fact, for any given delta Z, any length delta Z, and we can shrink that length down as we move, we see the shear strain is given by the angle gamma SZ. Shear strains, of course, we can interpret as angles. And of course, at any point in the cross-section, from the center of twist, we're rotating around that center of twist. And the amount we rotate now is going to be given in displacement terms of delta US. So this is a tangent displacement that corresponds with a differential length in the Z direction. Okay, and just to remind you, if I'm twisting only a small portion, it twists less in total displacement than if I'm twisting a long section. So this is that's what we're talking about here. The amount of actual twist. This is, you need to interpret this as a rate of twist, a rate of displacement per unit length in the Z direction. So what's interesting is if you look at this geometrically, there is now a relationship between the shear angle gamma and the amount of twist that occurs. And these things are constrained because the arc length that this thing sweeps through has to be held constant for any given differential length. So this radius times the change in angle gives us the amount of tangential displacement. Also, the delta Z times that shear angle gives us that amount of delta displacement. Since those two things have to be identical, now we can write a relationship between this angular change delta alpha and this shear strain. So let's do that mathematically now instead of just with physical argument. So recall the definition of strain. Gamma SZ was du ds. I should say dus dz. So the change in the arc length, this is an change in the displacement along the S direction with respect to Z, plus the change in the W with respect to S. Now, US is the displacement along the arc length. We're going to say that W, this is the out-of-plane warping, into the Z direction, and we're going to say that warping is small. And since warping is small, we can say that its derivative is negligible. So that gamma SC is essentially just going to be equal to dUs dZ. Because of those arc length continuity arguments that I made on the last slide, gamma SC times the differential length is going to be equal to the radius from the center of twist times the differential angle. And so we can now express this d alpha dz is equal to gamma sz over r, and we can take the limit of this as the differential lengths become small, and we can therefore express theta as being equal to gamma sz over r. Okay, if this is d alpha dz, this is the change in the total twist with respect to the z-axis, the derivative of the total twist with respect to the z-axis. So theta is the rate of twist, and it's now going to be equal to the shear strain divided by r. Okay, so this is just kind of a summative slide. We're bringing together several things now that we've already determined. One of them is that 2a is equal to r cross ds, the closed integral. Therefore, it's going to be equal to, and when we plug and chug, we're going to find that this is going to be equal to gamma sz over theta integrated over ds. And so from that, we can actually solve that for theta. Can say theta is equal to the closed integral of gamma sz over 2a times ds. Okay, so we've kind of got all the pieces together. Or I should say we have all the pieces of the puzzle. They're not entirely together yet. Now, what I mean by that is we can write a number of equivalent mathematical statements. So one of them will now be that the shear strain is equal to Q over GT. We've already determined that. We can substitute that in and pull out the constants. So now the linking is broken in the presentation. It should show up just fine in the online notes. But if we plug that calculation into this equation, what we get is this result. That is the rate of twist is equal to 1/2 Q over A, the shear flow over the enclosed area, times the closed integral of 1 over GT. So GT inverse here. And of course, we also know what Q is in this equation. So we could go ahead and plug that in. All right, so while you're capturing this as you're taking notes, what do we have? We have a rate of twist. Rate of twist. So it's the torque per unit length, or I should say it's the amount of twist per unit length. Rate of twist. What's it proportional to? Well, it ends up being linearly proportional to the torque that's applied. That sort of makes sense. It's going to be inversely proportional ultimately to the area, and it will, in this case, it'll actually, by the time you plug this in, it will be equal to 1 over, the area squared. Garrett, I see your question. I'll go back in just a minute, okay? So here's kind of the final version of all that plug and chug. So the rate of twist is equal, it's proportional to the torque. The more torque you get, the higher the rate of twist. It's going to be inversely proportional to the area enclosed squared. So the bigger you make that area, the amount of twist that occurs is going to decrease according to the inverse squared law. And it's proportional to the integral of 1 over gt. Now, of course, this is integrating around the arc length ds, so it's around the cell. Closed integral around the cell of 1 over gt. And with this equation, we can calculate a relationship that is substantively equal to gt. And then we can use that relationship much like we did when we did the solid cross sections calculations of torque. So this is the torsion equation. Gj theta is equal to t. That's Gj d alpha dz is equal to t. We've seen this equation when we did the solid calculations. This gives us a mechanism for calculating an equivalent Gj for this open section. All right, Garrett wanted me to go back to this slide, I think. Was this the one, Garrett?
Yes, thank you. All good though.
Okay, so I think we kind of have all these pieces now. I hope I didn't lose you along the way. It's actually turns out to be pretty simple. Okay, it's simpler than it seems. Let me do an example problem. Let's compute the torsional rigidity. So this is functionally Gj of two different cross sections, one being a square and one being a circle. We can make the assumption in this case that they have the same thickness. So knowing what you now know, which one is going to have torsional rigidity that's higher? Somebody take a stab at it. Garrett and Ethan both say square. I got a couple of people choosing circle. Scott also says square. All right, so we'll go through the calculation. But, look back at this equation. I'm going to underline the area squared portion of this pretty heavily. So if we have equivalent thicknesses, if the thicknesses are the same, then really we got to look at the area enclosed and say that that's really the biggest deal. So if they're the same thickness and they're the same geometric width, so you can think of this as being, all right, I've got an aircraft wing and I have a height that I can squeeze in a structural reinforcement, like a spar, and I'm going to try and choose between a circle and a square. Okay, and I want to make this thing as stiff as possible. I got a certain amount of area, I want to make it stiff. So if B is equal to D, this means that they're the same geometric width. The area of a square is, of course, going to be D squared. It's just, the area of a square. The area of a circle will be D squared over 4, so that's R squared times pi. Area of a circle is pi r squared. Diameter, radius is equal to diameter over 2, so we end up with this D squared over 4 times pi. So we have different areas. The area of the circle, of course, is going to be smaller. Pi 3.14 divided by 4 is less than 1. Okay, we can do this calculation for the rate of twist. Theta is the rate of twist. So it's equal to torque times the integral 1 over t times g ds. So this is an area, this is an integral around the domain, around its arc length. It's a closed integral, so it starts and it stops at the same spot. And of course, that's in the numerator. In the denominator is the area enclosed. So if we do this, well, so what do we know? We know that T is a constant. Okay, we say it's the same everywhere. We know that G is a constant. So that's the same everywhere. Because both of those are constants, they can actually be pulled outside of the integral. So we end up with this 1 over T times G times the integral, closed integral of ds. Well, what's the closed integral of ds? Well, that is just a measure of the circumference of the circle. Or in terms of the square, it is the total length as you work your way around the square. So for the square, that would be 4 times d. For the circle, of course, the circumference is pi times d. So that integral is very simple. We plug and chug these things now, and what we get is a GJ effective for the square, which this is just the torque equation. So, torque is equal to GJ times theta. This is the torsion governing differential equation. We can solve this for GJ. That means we move the theta into the denominator on the other side. And so GJ effective for the square is d cubed times T times G. GJ effective for the circle is d cubed times pi over 4 times T. And if we do the ratio of these two things, GJ effective for the square over GJ effective for the circle is going to be 4 over pi, which is going to be equal to 1.27 by the time we do the rounding. So if all we're interested in is to maximize the stiffness, what do? We increase the area. We try and enclose a greater area. That's how we increase the stiffness. Okay? In this context, the area of the square is larger than the area of a circle, so all other things being equal, make the area bigger makes it stiffer.
I have a question. Are those squares and circles enclosed with a hollow, or is it like a solid cross section?
Yeah, great question. This is all these calculations that we're doing now are for hollow cells. We call them cells because they're torsion cells. They are hollow cross sections. By the way, if we did this calculation otherwise, if it was not a hollow cross section, well, then what do we need to do? We need to calculate the J value, which is the integral of r squared dA, right? This is an r, not a sigma. So this is, for a solid section, we would do this calculation. By the way, we could do that calculation quite easily for the circular section and for the square section, and we'd get nearly identical results. Okay, but these for sort of these unusual cross sections that don't have nice circles or squares, then this calculation of J would be much more difficult in this equation than going through and calculating it the way that we have here. Okay, now, so I'm surprised no one has spoken up and complained a little bit, right? So let me do it for you. So, Dr. G, why in the world then do we usually see circular cross sections in optimal aircraft structures? Right? If you're saying the square for the same overall width is stiffer, why do we use circular cross sections? Right, and that's a fair question, and that actually gets us to the next example. Okay, if we want to use the same amount of material, right, what we're trying to do usually in aerospace structures is not just optimize or increase our stiffness. We're usually trying to increase our stiffness to weight, right? Our so-called specific stiffness. So if we're looking for the same material area and we have the same thickness of material, like if what we're buying has the same thickness, then which do we choose? Do we choose a square or a circle? Well, in this calculation, it's the same calculation, but it's going to be slightly different in its execution, because in this case, in order to make sure that the total cross-sectional area is the same, not the enclosed area, but rather the material area, for the same thickness, we can't have B and D being equal to each other. And the calculation for a square, so we'd have what? So D times 4 times thickness. This would be the material area for the square. Let's do B instead, because this is going to be a square with width B. We'll use D for diameter of a circle. So then we'd have a circle with a diameter D. So its circumference would be pi times D times its thickness would be the material area. So material area for a circle, pi dt. Material area for the square would be B, the width, times 4 times the thickness. Okay, so that's where these equations came from. Those are now material areas. If we equate these two things, then we can say that in terms of the diameter, we can solve for the width of the square. So for an equivalent amount of material used, the square will be of width B, which will be equal to D times pi over 4. So since 3.14 over 4 is less than 1, B, the width is going to be less than the diameter. Now, what about the enclosed areas? So now with the known values of B, area of a square is B squared. We now know what B is, so we square that. We get D squared pi squared over 16. The area of a circle is still going to be pi D squared over 4. And the integral that we did previously still ends up being the same in its functionality. You're integrating the closed integral of ds, right? Which now for B, for the cross sections that we've now defined, we can know the total length around the cross section. And so the GJ effective calculations for the square and circle end up being d cubed pi to the 4th times tg over 256. So this is for the square. For the circle, it's going to be the same as that we had calculated it before, d cubed pi tg over 4. We take the ratio of those things, we end up with pi cubed over 64, which when converted into a numeric value with 3 digits, I'm keeping 3 digits in this example, rounding to 3, I get 0.484. So what does this mean? This means the circle, in terms of specific stiffness per unit weight, the circle is about twice as stiff as the square. So if you just want stiff and weight doesn't matter, fill the area. If you want to make this thing lightweight and stiff, make it as close to a circle as you can. And in fact, increase the area. You can decrease the wall thickness. The larger the enclosed area is, the smaller you need the wall thickness to be to carry the same amount of stress. There is a limit there, of course. That limit is governed by buckling, which we don't really cover in this class. So just be aware that you can't make it infinitely thin. It will buckle like a sheet of paper. All right, questions on this? Any rule of thumb for this thickness? Scott asks. Boy, what a great question, Scott. A rule of thumb. That is a wonderful question. I would say that if you're starting to exceed 20 to 1 on the radius to the thickness, you've gotten really thin. Probably too thin. 10 to 1's probably in the right neighborhood. You can maybe get away with a little bit less. That's to avoid buckling, but there are a number of other factors that come into play, obviously. Well, you guys have had some insightful questions today. Great job, guys. Okay. We'll do another example here just for fun. This one's perhaps a little bit more realistic, although it's still not terribly realistic. Okay, this one starts to look a little bit more like an airfoil. Okay, so we're talking about a wing now. Now it's a terribly inefficient airfoil, as you can see, but nevertheless gives you an idea of what type of problems you might encounter. So in this example, we'll say that I have a total applied torque of 2 times 10 to the 4th. So that's 20,000 inch-pounds of torque. We'll say the overall length of this torsion carrying member is 100 inches, and I have 2 different materials that are present. I've got one in what I'm calling section A, and as you look at this, this is section A, and it's thicker. Okay, this is a thicker section. So not only is its material different, but its thickness is different. So we're going to say the material there is 5 times 10 to the 6th, so 5 mega psi. We're using, in this case, English units. That's the value of G. And in this segment here, we're going to say that it is a stiffer material. It has a higher shear modulus. In this case, we'll say 12 mega psi. Now, as I drew this, segment A is thicker. It's going to be twice as thick. It's going to be 0.1 inches thick versus 0.05 inches thick. The overall dimensions here are going to be 5. For the semicircle is going to have a radius of 5, and the sort of triangular section is going to have a horizontal length of 5. Obviously, it's got a vertical length of 10, which is twice the radius of the semicircle. Now, Scott, this doesn't necessarily follow that rule of thumb that I gave you. This is more for simple calculation than it is for realistic scenarios. I've not done a buckling analysis to determine if this particular structure, if we could make it this way, would buckle. But that's certainly something you would do if you were in a real-world scenario. Okay, so if I've set this problem up, what do I want to know? Well, what I ultimately want to know is the shear stress going to be high enough to cause a material failure? That's one thing. Number 2 is the rate of twist going to be too large? And then last but not least, I also want to know, what's the torsional rigidity of this thing? So we have just a couple minutes. We should be able to get through this really quickly. Here's your solution. Well, what's the shear stress? That's easy. That is equal to the shear flow divided by the thickness. Well, what's the shear flow? That's easy. That's the total torque divided by the area enclosed. Actually, 2 times the area enclosed. So we can calculate the area enclosed. I can do this just diagrammatically. So it's the area of this triangle, which is 1/2 base times height. It's the area of the half circle, the semicircle governed there. So that is these 2 calculations. It's pi r squared. That's the area of a total circle. So 1/2 of that plus 1/2 base times height. So the total area in this case is 64 square inches and change. So the total shear flow we just plug and chug gives us 155. And of course, shear flow is in units of force per unit length. It's a magnitude, pounds per inch. Now, as we think about our section here, we recognize that this is going to be constant everywhere around that circle. That is, the shear flow is constant. The shear stress is not. So the shear stress in segment A over here is Q over the thickness in that segment. And that works out to be 155. Notice the rounding here. I probably should round this a little bit more. It's not that precise, but this is what it is. The shear stress in segment B, because segment B is half as thick, is going to be twice as high. So 3,000 psi versus 1,555 psi, 3,100 psi. Okay, the rate of twist is this calculation. We've seen it now. 1/2 q over a, the integral of the inverse of gt around the around the circumference, what amounts to the circumference. So, you know, this, now we have to recognize that this integral, it is a closed integral, but it is a piecewise integral for this, right? If we look at our cross section, this integral 1 over gt ds. So g is constant, g and t are constant from here to here and from here to here, but then changes. So we can split this up into two integrals. We can do the integral from this point up to here, so we're going to call that one integral. We're going to do a second integral that is the integral around the remainder. Of course, the total integral is the sum of those two things. So if we look at this, as I break this up, this is the segment A, so it is 2 times the 2 arm lengths. So this arm length here is 5, it goes 5 horizontally, 5 vertically, so its hypotenuse is 5 times the square root of 2. This hypotenuse is 5 times the square root of 2, so we get 2 times 5 times the square root of 2. That's the arc length divided by GATA. And then continuing around, we're now looking at, you know, pi times r gives us the arc length, the half circumference of a circle, and that divided by g times b. And so from that calculation, very straightforward, gives us a rate of twist of 6.5 radians per inch times 10 to the minus 5. So what is the total angle of twist for the entire length? The length being 100 inches long. So this ends up being 6.5 times 10 to the minus 3 radians of twist. Last but not least, of course, we can calculate GJ, which is equal to torque over the rate of twist. And this works out to be 303 times 10 to the 6th in units of pound-inch squared per radian. That's everything that was asked for in the calculation. You can see now that what this has done, this set of equations, once we understand them and can then utilize them, turn out to be really quite simple. Quite simple, very straightforward for calculating things that you might otherwise think would be difficult to calculate. Do we need to know the shear stress? Yeah, you do. Is it really easy to calculate? Yeah, it is. So, you know, that works out to be really nice for us as aerospace engineers. Not many things in aerospace engineering turn out to be this easy. Right, that's a good place to stop. And quite conveniently, it's also the end of the lecture period. I'm happy to stick around for several minutes here, for as long as it takes really to answer any questions that you guys still have about the lecture so far. Otherwise, I will see you guys next week. Don't forget, the homework is up on Gradescope. Go ahead and get that in as soon as you can. And I'll see you guys soon.